Yeah, so thank you very much for this nice introduction and for the possibility to give here the introductory talk. As Hank already announced, I brought my own Kuipers Niederreiter book with me, and I can tell a little story to you. It's almost exactly 50 years ago when I learned what a uniformly distributed sequence is. I learned it in this room in a lecture by Wolfgang Schmidt, who was a visiting professor at this time at the University of Vienna. And I was in my first semester, and I thought I should see this famous person, and I attended the talk and the whole lecture. And after the lecture, I went to maybe after second or third week, I went to a bookstore which does not exist anymore. It was at Währinger Straße, where now this Magistrat building of the 9th district is. There was a bookstore, and I bought this version of Kuipers Niederreiter. And in the summer holidays, I tried to solve all exercise problems. And you see the book is almost gone, but it was very useful for me. Okay, so to be more serious, let me start with the lecture. And the lecture is devoted to metric aspects of uniformly distributed sequences. And in fact, I got interested in that kind of problems during these lectures of Wolfgang Schmidt. And these aspects have a long tradition in harmonic analysis. It goes back to the 40s and 50s. Zygmund, Salem, Gal, Koxma, and many other people worked on limit theorems for trigonometric series, and also then in the 50s for discrepancies of sequences. And I will show you the development of this metric theory of uniform distribution during the last 60, 70 years. Okay, so let me start. Since this is an introductory lecture, I start from the scratch. Let me start with the basic notions. I will focus on the very typical situation that we have points in very simple regions, say in the k-dimensional unit cube, and we count the points lying in given test sets. And my test sets are, as in the classical uniform distribution theory, are axis parallel boxes, and capital AN is the number of points up to index capital N lying in that box, and a sequence is uniformly distributed if an infinite sequence, if this counting number divided by the total number is asymptotically the Lebesgue measure, so the volume of this box. In the whole lecture, I will be interested in quantitative aspects of uniform distribution, and my measure for studying these quantitative aspects is the discrepancy. And there are many notions. Of course, you can take any norm to measure this difference between the counting measure and the Lebesgue measure, but I take the supremum norm over all these test sets. And it's an easy exercise. In fact, it was one of the first exercises I did in the book to show that the sequence is uniformly distributed if and only if the discrepancy tends to zero. One direction, of course, is trivial. The other direction is simple topology. But it's a nice exercise. Okay. Clearly, also, the discrepancy is a quantity lying between 1 over n and 1. also very simple to see this, since any box has at least one, you can choose a box having at least one point inside, and taking the box arbitrarily small, you get the lower bound, and the upper bound is completely trivial. But when I attended this lecture 50 years ago, Wolfgang Schmidt, in the second week, I think, proved his famous result, namely that for an arbitrary sequence, infinite sequence, one always has the lower bound of the order log n over n for infinitely many n. This has a long history. This lower bound, it's also a name which was not mentioned by Henk, van Ardenne Ehrenfest, a Dutch person who was the first who showed that, in fact, 1 over n cannot be, so 1 over n can significantly improve by a term phi of n over n, so that phi of n tends to infinity. The first term she found was, if I remember correctly, square root of log n or something like this. Yes? And step by step, this lower bound was improved. And of course, Wolfgang Schmidt's lower bound is best possible. If you take a quadratic irrational, for instance, and taking the multiples of these quadratic irrationals, then you get a sequence which has, in fact, which attains this lower bound log n over n. So the discrepancy of that sequence is log n over n. When Michael Drummelter and I wrote our book, we studied this, the history of these bounds, and in fact we found a citation of André Schinzel, which is not widely known. Usually people say, okay, log n, the sequence n alpha has a discrepancy log n over n if alpha has bounded continued fraction expansion. That's true, but this is not necessary. This is sufficient for log n over n. André Schinzel found by some reformulation of old work of Alexander Ostrovsky that it is possible to characterize exactly when sequences n alpha have this best possible discrepancy bound, and the characterization is very nice. If alpha has continued fraction expansion, say a0, a1, and so on, then this optimal discrepancy bound is equivalent that the arithmetic means of these denominators are bounded. Of course, this is a weaker condition than assuming that the coefficients a, j itself are bounded. Yes? So this is a characterization, which is not quite easy. But it follows from Johannes Scheussengeier's general formula for the discrepancy. And it should also mention here that Johannes Scheussengeyer, who is not here, had proved the explicit formula for discrepancies of such sequences. And from this formula one can get that, but it was known earlier by earlier results of Ostrovsky. So after these little historical remarks, let me come to more recent things. So Klaus Roth, the Fields medalist, got the general lower bound for discrepancies in arbitrary dimension. You see, in dimension 1, this is weaker than Wolfgang Schmidt's bound. It's square root of log, and the best possible bound is log. but it's a bound for general dimension, and he invented a very beautiful general method, the orthogonal function method, introducing Rademacher's system and working out this asymptotic inequality. Constructions show that sequences exist with discrepancy log n to the k. Yeah? So there are simple constructions for so-called low discrepancy sequences. These are sequences where the discrepancy is in log n to the k over n. And simple constructions are multidimensional versions, and this is another Dutch name of van der Corput sequence. Yeah, van der Corput sequence is, I should be careful with time. Van der Corput sequence is the following: you take a number n with digits epsilon j, say q to the j. So in Q-ary system, Q is 2, 3, and so on. And then you define a van der Corput sequence with respect to base Q. With respect to base Q of n, it's just reflecting the digits on that decimal point. Yes, so it's epsilon j over Q to the j plus 1. Yeah? So you get a sequence in the unit interval, and doing that for distinct, say, prime basis Q, you coordinate-wise, you produce a sequence which satisfies this very nice bound. The computer doesn't like that I use the blackboard. Yeah. Okay. Good. I don't like the computer, so I continue without the computer. Okay. So these are so-called low discrepancy sequences. And yes, the Ross bound, without having it here, of course, I have to change. The Ross bound, which is this lower bound, with some dimension constant, log n to the k half over n, for infinitely many n, nowadays is known that it can be improved. Yes? So, of course, in dimension 1, it's Wolfgang Schmidt. But in arbitrary dimension, it is a long-standing open problem to find the correct bound. You see, construction gives this, lower bound is this, there is a gap of k half in between. And some people believed in the old days that this is the correct bound. Some people believe that this is the correct bound. What is known nowadays is a very fundamental work by Mike Lacey and Dimitri Bilik and others, who could improve this lower bound of Ross by some little quantity in the exponent. Yes? If I remember correctly, in dimension 3, the little quantity is 1 over 8. Yes? And this was known by Beck earlier, and then it was done by this group around Mike Lacey. Okay, so of course, uniform distribution is a concept which is related to randomness properties of sequences. And of course, randomness properties of sequences are also of interest for theoretical computer scientists, but they are more interested in discrete sequences, 0-1 sequences or +1, -1 sequences. And clearly, you can construct a discrete sequence from a modulo 1 sequence of numbers just by looking, for instance, is the most simple way to do this. If the elements of the sequence lie in the left side of the interval or in the right side, you write +1 or -1, and you get the +-1 sequence in this way. And such kind of random properties or pseudo-random properties of discrete sequences were studied in the last, say, 30 or 40 years by András Sarkozy, Christian Maudoux, and related people, and they introduced a set of quantities measuring these pseudo-random properties of sequences. You see, uniform distribution is a very, very weak property measuring pseudo-randomness. If you have two uniformly distributed sequences, this is the unit interval, and this is 1/2, and you have a uniformly distributed sequence here, say yn, and a uniformly distributed sequence on the right-hand side, say Cn, and you construct the sequence xn, saying for even indices it's this one, and for odd indices it's this one, and you look at this possibility to make a discrete sequence, you get a periodic sequence. Yes, so and this has nothing to do with randomness. Yes, so uniform distribution is a very weak concept, and so people thought to sharpen this concept. For instance, András Sarkozy and Christian Maudoux introduced so-called well distribution along arithmetic progressions. So they looked at the distribution behavior at any arithmetic progression inside a given sequence. And then, if this quantity is small, this is of course a much stronger concept of pseudo-randomness. Another possibility is the so-called complete uniform distribution or infinite uniform distribution, as it is written here. This is the following concept. Take a sequence, and we are not only counting single elements lying in a test set, we are counting blocks of subsequent elements. So, blocks of length 2, blocks of length 3, and blocks up to blocks of length k. And we count how many of these blocks lie in a k-dimensional box, and if these blocks are uniformly distributed, then we say the sequence is completely uniformly distributed or infinite uniformly distributed. And it turns out that this concept is, of course, known to be very old. In fact, it goes back to Émile Borel, so beginning of the last century, who introduced the concept of normal numbers. Yeah? So a number is normal in base Q, so in such a number system, if all digits show up as asymptotically. So a number is now in the unit, so a real number, not an integer, real number. If all the digits show up with the correct frequency, 1/q, because we have q digits. But not only single digits, also blocks of 2 digits. blocks of 3 digits, and so on. And of course, you can ask difficult questions. Is square root of 2, for instance, a normal number? Is pi a normal number? So all these questions are unknown. It's the very difficult questions. But you can also ask, do there exist normal numbers? This is a much simpler question. You can give answers of the different kind. For instance, Emile Borel answered this question by proving that in the sense of Lebesgue measure, almost all numbers are normal. And he did it very directly by counting. Of course, people knowing ergodic theory can answer the question immediately. It's a simple consequence of the Birkhoff ergodic theorem. Since the transformation Q goes to fractional part Q times X is an ergodic transformation, and from this everything follows. Of course, it's a much more subtle question to construct normal numbers. It's easy if you want to construct normal numbers for a given base. This is also a very nice exercise problem. Champernowne's number. Yes, you can look at the number, say, 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on, writing all the positive integers, one after the other, and by simple counting arguments, you can show that this is a normal number in base 10. Similar construction work for other bases. But if you want to construct a number which is normal, one and the same number, which is normal in any base, this is much more subtle. And this can also be done, but this is beyond the simple exercise problem. And yeah, in the next lecture, Veronica maybe addresses this problem. She had a very nice result with colleagues showing that it's possible to construct such so-called absolutely normal numbers with the help of a polynomial time algorithm. And this was an old problem arising in theoretical computer science. Okay, so I don't say more on normal numbers because the expert speaks in the next talk. And I already mentioned there is a zoo of properties which can be used to characterize pseudo-randomness of sequences. I already mentioned the well distribution measure along arithmetic subsequences. I already mentioned normality, and Christian Maudoux and Andras introduced normality measures and proved several constructions for this. I cannot give more details here. I only want to point out a very, very strong property for describing pseudo-randomness. This is a property which was introduced by Donald Knuth in his book on the art of computer programming. And this is the strongest concept he introduced in this book concerning pseudo-randomness. And the definition was just taking a sequence, taking subsequences for any computable choice of the indices. So you take a computable subsequence of the positive integers as index sequence of the sequence xn, and if for any choice, for any computable choice, this sequence is normal, so completely uniformly distributed, then it satisfies this definition. So, of course, this is a very, very strong property. And Knuth asked the problem, do such sequences exist? And in my first work with Harald Niederreiter many, many years ago, we could prove this conjecture of Knuth in an unfair way, of course. The unfair way is again probabilistic and measure theoretic. We could show that the sequence x to the power of n satisfies this definition for almost all x real numbers bigger than 1. And this is a very delicate probabilistic argument, but nevertheless it gives an answer, and by some logical considerations one can see that it's impossible to construct such sequences algorithmically. So the problem of Knuth is a very academic problem. Yes, so it does not help computer scientists to find such pseudo-random sequences. But nevertheless, this work in the 80s was the spirit for further developments in this probabilistic theory of discrepancy, and I will show you the outcome now in the remaining part of my talk. I should also mention it's possible here not only to consider blocks of digits of fixed length k, you can consider blocks of growing length. So the block length k can be dependent on n, slowly growing, and even there you can show that such sequences exist by probabilistic arguments, if the block length does not grow too fast. Yes, this is one of my older papers. Okay, so let me come to some very modern developments in this theory, and for details I refer to the very, very recent survey paper by Christoph Aistleitner, myself, and Istvan Berkes. It appeared in the Société Mathématique de France series Panoramas and Synthèses, a long paper with also some new results concerning limit laws for lacunary sequences. So another possibility to characterize random properties of sequences, of course, is to look for properties which are very well known for true random sequences, for IID in sequences. And if a deterministic sequence has these properties, you can consider it as a good model for a random sequence. And I will focus in this talk on just one property for true random sequences, and this property is the law of iterated logarithm. Known from standard classes in probability theory that an IID sequence satisfies a law of the iterated logarithm, and formulating this for discrepancies, one gets this limit law of Jung and Smirnov, for instance, saying that such a random sequence xn has a discrepancy dn satisfying this law, square root of n over square root of 2 times log n, and the lim sup here is exactly 1/2. You can compute this lim sup, it's exactly 1/2. And it was a very well-known problem of Paul Erdoes in the early 60s, asking whether such property also holds for given sequences. Yes? For instance, for these sequences which were studied in harmonic analysis very intensively, namely these so-called lacunary sequences. So alpha is a real number, and j is a lacunary sequence, say, of integers. Lacunary means exponentially growing. The simplest example is the example known from the theory of normal numbers. Q to the j. If Q is a base, a number is normal if and only if alpha times Q to the j, or Q to the n, is uniformly distributed mod 1. Yeah? Alpha is normal with respect to base Q if and only if this sequence is uniformly distributed mod 1. And so this is an extension of normality with a very precise information on the discrepancy in a probabilistic way, namely for almost all alpha. If you construct normal numbers, for instance, this Champagnat number, maybe Veronica will give such answers here, the discrepancy is much bigger. So the distribution is worse than the probabilistic, than the typical way. Yes? So usually here you get discrepancies 1 over log n. Not log n over n, 1 over log n. So very big discrepancy. In the probabilistic way, you get at least 1 over square root of n times some double log factor. Okay, and I will give now very new results on this, in this area. You see, normal numbers are related to exponential sequences. Q to the n. Q to the n is a semigroup generated, a multiplicative semigroup generated by one number, Q. It's a lacunary sequence, growing exponentially. Of course, you can extend this construction by taking, say, tau distinct primes, or tau coprime integers, and taking the multiplicative semigroup generated by these numbers. 2 and 3, for instance. Ordering these numbers with respect to growth, you produce a sequence nj, and you can ask the same questions like for q to the j. You should be careful. If one looks in the book of Hardy-Littlewood-Polya, which is maybe known many generations of students, problems and theorems in analysis, you can find an exercise problem, in fact, showing that these sequences are not anymore lacunary. They are exponentially growing only in the case when the set of generators consists of one element. But nevertheless, they are growing faster than polynomial, and in fact, this theory applies also for this kind of sublacunary but super polynomial sequences. And I will show you results, metric results for discrepancies and for mean values of function evaluations with respect to functions which are nice. So regular, at least of bounded variation, but sometimes it's also good to have differentiability properties. The proofs depend in most of the cases on an exponential sums and estimates for exponential sums. I wrote here one of these basic inequalities. This is the Erdoes-Turan-Koxma-Süß inequality, an extension of this Erdoes-Turan inequality in one dimension. If one has studied proofs of this, the proofs always depend on kernels, on positive kernels in harmonic analysis, and refinements, more refined approaches often can be given by considering better kernels than the kernel which was originally used here. The kernel which was originally used here is Feyer kernel, and there is Selberg kernel by Berling-Selberg kernel, which was introduced to such problems by Jeff Waller, and applying these kernels directly sometimes gives better results. And what are better results? Better results are results which give this lim sup for discrepancy or for function evaluations as an explicit value. Not only showing that this lim sup, as in the standard law of iterated logarithm, is bounded by constants, positive constants. This was the original problem by Erdoes. But what we were interested in is to compute the constants. You have seen for true random sequences by Chung-Smirnov, the constant is 1/2. Here it's possible to compute the constant. It's also possible to show that the constant is 1/2 if this sequence nj, you remember we considered sequences alpha times nj, nj is this lacunary sequence. If this sequence is more than exponentially growing, so superlacunary, that means that the quotients tend to infinity. So if nj plus 1 over nj tends to infinity, in this case, again the constant is 1/2. But as I told you, for the normal numbers, the quotient is q, it does not tend to infinity. And for the Hardy-Littlewood-Polya sequence, it's not exponentially growing. So the quotient tends to 1. And so 1/2 does not come out by such arguments. So, and of course in mathematics we always, as Hilbert said, we should always think what is the truth. And here we can answer, this is a difficult question, yeah? So in particular in politics. But in mathematics it's easier. And in this case it's definitely solved. One can compute the constants. And here you see the magic values. And please do not ask me why these numbers show up. It is a serious computation with moments, and one has to consider big moments and big integrals, and after hard work, one gets, for instance, the nicest constant is, of course, the constant for q equals 2, which is the normality constant for base 2. It's square root of 42 over 9. Don't ask me why. For other systems, for these Hardy-Littlewood-Polya sequences, here you see the constant. The constant is this product over the basis q. And what I should remark here, and as I told you, these details you can find worked out in our survey paper, there is a significant difference between limit laws for discrepancies and limit laws for function mean values. That significant difference is the following. For discrepancies, the limiting constants depend on the ordering of the sequence. So if you permute elements, you get another distribution behavior. Of course, in probability theory, if you permute an IID random sequence, you get the Chung-Smirnov again. This doesn't matter. But in our case here, these are deterministic sequences. If you permute them, the discrepancy limit law is not invariant under permutations. You get different constants. However, the limit law for function evaluations against regular function, it's independent of the ordering. So the constant is always the same when you permute the elements of the sequence. Yeah? And why is this the case? Okay, yeah, the case, and I turn back what I learned in Wolfgang Schmidt's lecture here 50 years ago. The main tool for doing this is Wolfgang Schmidt's subspace theorem and extensions which were found in the last years. I will show you, since there are not all are very familiar with these Diophantine geometries, tools. I will show you in the next slide some details. But the problem is, if you look at this Erdoes-Duran-Koxma inequality, to prove that the discrepancy is small, you have to show that exponential sums are small. Exponential sums are not small, they are big if the exponents are close to 0, modulo 1. Because these are e to the 2 pi I times something. So you have to look at situations when the exponents vanish. And the exponents here are linear combinations. This is an inner product. And we take P's moments, as I told you. So you have P-fold integrals. And this means that the exponents vanish if such linear Diophantine equations are satisfied. And the entries of these equations come from I have written it for this Hardy-Littlewood-Polya sequence, are in the language of Diophantine number theory. These are elements from the semigroup S, so these are S-unit equations. One has to count solutions of S-unit equations, and during the last decades, really heavy machinery has been developed, and for instance, for this problem, a nice result of Amoroso and Viada workout, one can show that such equations have a number of solutions which can be explicitly bounded as it is written here. Yes, and this bound helps to compute everything. One can estimate the exponential sums, one can compute the constants. Okay, so what is subspace theorem? Okay, so just some few final comments. Subspace theorem, in fact, is a multidimensional version of the Huesiegel-Ross bound in Diophantine approximation. So it's a theorem saying that a product of independent linear forms satisfies if that satisfies such an inequality, so if this product in absolute values is less than norm of x to minus epsilon, so the norm is the maximum norm, and the absolute value is at the moment the standard absolute value, and if such a estimate is satisfied, then x is a vector in n dimensions, n bigger than 2, then it's only possible that these solutions lie in a finite number of proper subspaces of the n-dimensional space. Yes? And it's very important that these are linearly independent linear forms. And for instance, if you take the case n equals 2, if you take the case n equals 2, and you can see if I multiply alpha minus y over x by x, I get, or better by x squared, I get x times alpha x minus y, and I multiplied by x squared, c dependent on this number epsilon, over x to the epsilon. You see these are two linear forms. If alpha is an algebraic irrational, I have written it here, it's easy to see that these linear forms are independent. So applying and doing some easy calculations, applying this general theorem on linear forms for this specialization immediately gives the Ross inequality from Diophantine approximation. So this is really a very, very heavy tool, and it is of a very general shape. It can be also extended replacing the Archimedean absolute value by p-adic absolute values. This was done by Schlickewey, and it can be generalized very, very deeply to finitely generated groups, which is a very recent development by Curie and Evertse. Some very few years ago, they published a very nice book on that, and it has a lot of consequences. For instance, the consequence 4 here, if you have algebraic numbers, a linear form in algebraic number satisfying this Diophantine inequality, C over norm n to the minus 1 plus a small delta, has only finitely many solutions. So you can count the solutions, but I should say one important thing here. You can count the number of solutions. There also exist quantitative aspects of these results. You can give bounds. As I showed you this result of Viada and Amoroso, you can give bounds for the number of solutions, but you don't get bounds for the size of the solutions. So these are highly ineffective results in the sense that it is not, even if you know that there are at most 2 solutions, you don't have an algorithm to decide whether there is a solution or not. Because if you start to compute the solutions, it may happen that your algorithm doesn't end. Yes? So this is a very, very beautiful result, but it does not give you algorithmic approach to the solution of that problem. Okay, but where are the consequences? For instance, for Kronecker sequences, which are the immediate multidimensional extension of this n-alpha sequence, multiples of an irrational alpha, you can take a number, a vector alpha, with components alpha 1, alpha m, m components, which are linearly independent algebraic numbers over the rational, linear independent algebraic numbers. You can, by applying this consequence 4, immediately an upper bound for the discrepancy. You see, this is not anymore log n to the k over n. It's n to the epsilon over n. Of course, you can say epsilon arbitrary small. That's nice, but for a number theorist, there is a big difference in saving a power or saving a logarithm. So this is, of course, nice. But, of course, it's in some sense weak. We use a heavy tool to get this bound of discrepancy. However, and I return to my words on Wolfgang Schmidt's lecture. Wolfgang Schmidt, in his lecture at that time, 50 years ago, showed that for such multidimensional sequences, we get for almost all alpha, so in this probabilistic metric sense, the discrepancy bound Pn of alpha n is big O of log, you see, n to the, and what Wolfgang Schmidt did in his lecture was this. It was one of his important results. You see there is a difference, m plus 1 and m, and it was later in the 90s. You see how old I was. This was in 70s, whatever, 5, and it was very new at that time. And there was this improvement from m plus 1 to m. And this is an annals paper by Beck. And it is an annals paper, and I have never seen that, which appeared twice. The paper appeared with 1 million of misprints, lower bound maybe, and it was not due to the author. And so the editors or whatever who did the administration there overlooked that there were corrections and so on. So this paper appeared twice, then with corrected misprints. And but it is a very beautiful paper, and this is of course optimal, this exponent. And let me end. I said a lot of developments, but I only indicated very briefly the contributions of the French school to this area. The French school is very heavily influenced by, of course, the work of Gérard Rossi and his approach to sequences via substitutions, and so related to fractal geometry. And I will end here with a very beautiful paper which also uses the subspace theorem in a very significant way. So this is a powerful method for various problems of that kind. And this is a paper, it's also an annals paper by Adam Czeski and Jan Peugeot, and there are also Ferenczi, Modui and others related to this kind of problems. It is devoted to estimates for the so-called subword complexity. You see, a normal number is a number where, of course, all blocks show up with the same frequency q to the k, if k is the block length. At least any block shows up. All blocks show up. And the subword complexity, pk, is the number of distinct blocks of k digits which show up. The number of distinct blocks. And of course, the maximum number is, if it's a binary sequence, 0, 1, it's 2 to the k, or in general q to the k. But of course, there also exist sequences with a much smaller pk. And the smallest are very well known in dynamical systems. These are the Sturmian sequences. For instance, the Fibonacci word, yes, is a typical example of such a Sturmian sequence. And I suppose that people will give lectures concerning this. And by means of subspace theorem, it's possible to prove this result, that the lim inf of p to the k, or p of k or p of n, I don't know what I have written on the screen, p of n, the lim inf of p of n over n is at least infinity if the number is an irrational algebraic number. So for algebraic numbers, one cannot get a Sturmian sequence, because a Sturmian sequence is the lowest, the smallest subword complexity, which is n plus 1, which is linear. And for algebraic numbers, it can be shown by subspace theorem that it cannot be linear. The lim inf has to go to infinity. So, thank you very much. This is the end.